In question 1a, we need to complete this equation to show the beta-minus decay of protactinium. Well, in beta-minus decay, a neutron becomes a proton, so the proton number or atomic number here must have been one smaller. The mass doesn't change, and we also have an electron anti-neutrino. So we end up with the protactinium with a mass of 233, the same as the uranium, and an atomic number of 91. In B, we have this table to complete, and we're told there are two other nuclei, P and Q, which can also decay into uranium-233. P decays by a beta plus decay to produce 23392 uranium, and Q decays by alpha decay. We need to label the positions of nuclei P and Q. Well, in beta plus decay, a proton becomes a neutron, so we would have a higher proton number and a lower neutron number, so P would be here. In alpha decay, we lose 2 protons and 2 neutrons, so we would start 2 protons higher and 2 neutrons higher, so Q would be here. In C, we have this typical fission reaction, and in part 1 we need to find the number of neutrons, x, given here. Well, the number of neutrons on the left-hand side is, for the uranium we have 233 of the atomic mass minus the 92 protons, that's shown here. There's one extra neutron here, so we have 142 neutrons on the left-hand side. We must have 142 neutrons on the right-hand side. For the krypton, we have 91 minus 36, shown here. For the barium, 139 minus 56, shown here, and also x. And this must come to 142, the same as on the left. So x is 4. In part 2, we need to find the energy released in megaelectron volts in this reaction. Well, first to find the mass defect in atomic mass units, we're given the mass of the uranium, the mass of a neutron. We must remove the mass of the krypton and the barium, and the 4 extra neutrons. This gives a mass defect of 0.18136 atomic mass units, and each of these has a value of 931.3 megaelectron volts, given on the formula sheet. So this comes out at 169 MeV.